Alright, hello everybody. This video is going over the structure 2.1 and structure 2.2 practice questions from the textbook. I will upload another video going through 2.3 and 2.4 later today. I thought it would be easier to split them up in case you didn't have multiple hours to watch a video. So here we go. For our first question, it says, which element does not generally form ions during chemical reactions? Well, we know when we are talking about forming ions for chemical reactions, normally we're talking about metals and nonmetals, and our metals are going to give up electrons or donate electrons, forming a positive charge, and our nonmetals are going to accept electrons and therefore having a negative charge. Now I hope that you look at these four options and see carbon right away as the answer, because carbon doesn't generally form ions due to it being more stable when it shares electrons to form those covalent bonds. So you know how when we're doing Lewis structures and we always say, okay, carbon, where is it going to be? It's going to be the central atom because it forms 4 bonds. Well, it would require a lot of energy for carbon to lose 4 electrons or gain 4 electrons. So it typically doesn't do that. It typically forms molecules instead, which we've seen so much in your chemistry journey so far. So the answer to this question would be carbon. I do really quickly want to go over charges of elements. If you are comfortable with this, you can go ahead and kind of skip forward, but I do want to make sure that we understand the basics of forming ions. So remember, when we have our group 1 elements, our group 1 elements have 1 valence electron. So when a group 1 element wants to react, obviously it wants to become stable. And with 1 valence electron, it's highly unstable or highly reactive. And the reason being is it only needs to lose 1 electron in order to become stable with the previously full octet. So when it gets rid of its 1 valence electron, now it has 1 more proton than electrons. Because remember, they all started with the same number of protons as they did electrons. So for example, if we're talking about lithium, lithium has 2 electrons in the first energy level and 1 in the outside energy level. So at the beginning, it has 3 protons and 3 electrons. But when it gets rid of this outermost electron, now instead of having the same number of protons as electrons, it has 3 protons and 2 electrons. So there's an extra positive charge, which is why all of these group 1 metals form a positive 1 charge when becoming an ion. And our group 2 elements are pretty much the same concept. We have an element with 2 valence electrons. And remember, stability is 8, an octet, right? So do you think this element is going to gain 6 electrons to become stable, or is it more likely to lose 2? Well, it would require way less energy to lose 2. So it donates those outside electrons and it goes back to its previous full octet, which is much more stable. So because it loses 2 electrons, now these elements have 2 extra protons, which is why our group 2 elements form a positive 2 charge when they become an ion. Now our transition elements down here in the D block of the periodic table, they're a little bit different in terms of reacting because they can obtain multiple charges or multiple oxidation states. But the key thing to remember with our transition metals is all of them, both the D block and the F block, every single one of those elements start off with 2 valence electrons. And that's because they have a previous S sublevel that is full in the outermost energy level before they go back and fill in their D or their F sublevels in lower energy levels. So just remember, the first 2 electrons that are removed in a transition element are going to be from the outermost energy level in the S sublevel. So, and we'll talk about that a little bit more because we do have a few questions on that in this video. And so if we go back to our trend that we're talking about, like aluminum and gallium, Those have 3 valence electrons, so those are going to lose those 3 valence electrons when they become an ion. So our group 13 elements are most likely to form a positive 3 charge. And then we move into our nonmetals. Our nonmetals have more than 4 electrons, so they are most likely going to gain electrons in order to get to that 8 or full octet. So like nitrogen and phosphorus, for example, those have 5 valence electrons, so they want to gain 3 electrons, which would give them a negative 3 charge. Oxygen, sulfur, selenium, those would have 6 valence electrons, so they want to gain 2. Remember, electrons are negative, so when you gain them, they give a negative charge. And then finally, our group 17 elements have 7 valence electrons, so they only need to gain 1 when becoming an ion to be stable. Okay, number 2, which statement is true for most ionic compounds? So the first one, it says they contain metal and non-metal elements. That is 100% a correct statement. When you have an ionic compound, that is going to be an electrostatic attraction between a positive ion and a negative ion, which, if you talk about metals, metals are going to lose those electrons, so metals are going to have a positive charge, while your nonmetals are going to gain the electrons, those would have your negative charge. So this would be a true statement, so I would be correct. So you could go ahead and cancel out C as your option. Then we have number 2, they conduct electricity in the solid state. So this is not correct. And the reason being is when you have a solid ionic compound, they're not going to conduct electricity because their ions are fixed in place within the crystal lattice and they can't move. So electrical conductivity requires free moving charged particles, which are only possible when the compound is melted or dissolved in water. So you'll either see it saying a molten state or aqueous or dissolved in water. So when an ionic compound is either melted, molten, or dissolved in water, then it can conduct electricity, but in the solid state, it cannot conduct electricity. So 2 would not be correct, so that cancels out A and D. So you're left with your choice of B, but let's go ahead and read number 3. They have high melting points and high boiling points. That is, in fact, a characteristic of ionic compounds. All right, number 3 says, which electron transfer describes the reaction between aluminum and oxygen? So these are stable atoms over here. They are currently at a 0 charge. When we go over to our ionic compound, we know that they obtain charges in order to form that ionic bond. So aluminum, we know, creates a positive 3 charge. Oxygen, we know, creates a negative 2 charge. Remember that positive 3 means that aluminum lost 3 electrons, because remember, electrons are negative, protons are positive, so it has 3 more protons than electrons now. So aluminum would lose 3 electrons, and then oxygen would gain 2 electrons, because it has a 2 negative charge. So all of these options are talking about losing electrons, so we know we're going to be talking about aluminum, and we know that aluminum lost 3 electrons, so B would be the correct answer. All right, so for number 4, we're given 3 different substances, and we're giving their melting point, their boiling point, and their electrical conductivity as an aqueous solution. And then we have 3 different options for X, Y, and Z. We have calcium oxide, which is an ionic compound. You should know that calcium forms a 2 plus charge, oxygen forms a 2 minus charge. Then we have sodium bromide, which is also an ionic compound because we have that electrostatic attraction between oppositely charged particles. And then finally, we have silicon dioxide, which if you don't know at this point, please write it somewhere in your notes. Silicon dioxide is a covalent network solid, which is something we'll talk about more specifically on the next slide. All right, so let's dive into the different types of solids and their classifications based off their bonding types. So the first one are metallic solids. Whenever you get a question and it says that it conducts electricity as a solid, that should immediately point you in the direction of a metallic solid, which are just metals bonded together with metallic bonding. Now remember, metallic bonding is when you have your cations or your metals They formed a cation, which means they released their electrons, and those electrons are flowing through as a sea of delocalized electrons. So they can conduct electricity in a solid state. When we're talking about metals, they do have very high melting points. Just keep that in mind. Then we have our ionic solids. Remember, ionic compounds are going to be anions and cations held together by their electrostatic attraction between the positive charge and the negative charge. When we're talking about ionic solids, they do have pretty high melting and boiling points. They are brittle, they are hard, and as a solid, they do not conduct electricity. Now keep in mind, when ionic solids are dissolved in water, which most of them are soluble, when they're dissolved in water, they're going to split apart into their positive cations and their negative anions, and at that point, they will be able to conduct electricity. Then we have our covalent network solids. That just means that you have essentially one giant molecule. Now, a lot of the IB mark schemes will say instead of a covalent network solid, it'll say a macromolecule. It's essentially the same thing. You have a element or a compound, and instead of just being by itself and having a whole sample of a bunch of these molecules, they all bond to each other. And I'll give you some examples on the next slide. So our covalent network solids, just keep in mind, they have extremely high melting points and high boiling points, but they do not conduct electricity under any circumstance. And then finally, we have our molecular solids. These are just held together by intermolecular forces. They have very low melting points, and they also do not conduct electricity. So the difference between these two options would be that your covalent network solids are going to have much higher boiling point and melting points than your molecular solids. All right, so these are the examples of the covalent network solids, ones that you should definitely have on your list to just keep in mind for your IB chemistry exam because they are quite common. So the first are your 3 allotropes of carbon. Allotrope just means that you have a form of chemical element that can exist in multiple arrangements of atoms that can have different chemical and physical properties. So carbon is one of those allotropes. It has 3 of them. They are diamond, graphite, and fullerene. And then we also have silicon dioxide and silicon carbide. So you can see all of these molecules or elements are all put together by bonds. So they are essentially one giant covalent molecule. Okay, and then the last thing I want to talk about, because we have 2 ionic compounds as our options in this question, is Coulomb's law. Now remember Coulomb's law, the formula is over here. Coulomb's law is relating charge of particles, and it's also relating radius of particles. Now, charge is the first thing that you need to look at when you are comparing ionic compounds, because charge is the most important one, and it creates the most difference in force. So if you're looking like at the example over here with sodium chloride and aluminum chloride, because aluminum has a greater charge than sodium, aluminum chloride would automatically be a stronger attraction, which means it would have stronger bonding, which means it would need more force to break it apart. So if you are looking at ionic compounds that have the same charge, and then you still want to know which one has a higher boiling point or a higher melting point, then you would look at radius. So if it has a shorter radius, then it's going to have a stronger attraction or stronger bonding. And that should make sense, right? Because if it has a shorter radius, then that positive cation can get closer to the negative anion and create a stronger bond. So let's go back to our question. Okay, so let's start with our ionic compounds. So we know that X and Z have to be our ionic compounds because they're the only ones that are conducting electricity as an aqueous solution, which means we know Y is automatically our network covalent or silicon dioxide. So automatically you should be able to cancel out C and A because Y is not the network covalent. So then we are looking at calcium oxide and sodium bromide, and we are comparing X and Z. Now, if we go back to Coulomb's law, remember, the higher the charge, the more force it requires to break it apart, which would mean a higher melting and boiling point. Now, since calcium oxide is a positive 2 charge and a negative 2 charge, that means it's a higher charge, which means it would require more force to break it apart, which means Z, because Z has a higher melting and boiling point, Z would be calcium oxide, and X would be sodium bromide. So D would be our answer here. All right, number 5 says, what is the formula of barium phosphate? So barium is actually not on this periodic table. It's right below strontium. But barium is in group 2 of the periodic table, which means it has 2 valence electrons and forms a positive 2 charge. So barium has a positive 2 charge. Phosphate, remember, if it was phosphorus, it would end in phosphide. So A and C should have been automatically canceled out. And then if you remember your phosphate polyatomic ion, it is PO4 with a negative 3 charge. If you do not remember your polyatomic ions, please take a screenshot of this chart here and start memorizing because you are going to need it. So then from here, we need to balance out our charges. Now you could use the cross method, which means the 3 would go to barium, the 2 would go to phosphate, or you could know that the common multiple of 2 and 3 would be 6. So to get barium to a positive 6 charge, we would need 3 of them. And to get phosphate to a negative 6 charge, we would need 2 of them. So the answer would be B. Which substance shows the most ionic character? So ionic character affects a compound's properties in a few different ways. The first one with electrical conductivity in aqueous solutions, compounds with a higher ionic character are going to dissolve into free ions, which is going to allow them to conduct electricity. So if we're talking about ionic character and electrical conductivity in aqueous solution, we know it's going to be high. So A and B, we're automatically going to cancel out for this. And then let's move on. Since solubility in heptane is the same answer, I personally would have moved on to volatility. But just to make sure we understand, heptane is a non-polar solution. Ionic compounds dissolve in water really well because water is polar and has positive and negative ends. And when ionic compounds dissolve in that water, those anions and cations are attracted to those positive and negative ends of water. Well, in heptane, it doesn't have that. So it's not going to be very soluble in a non-polar solution. So it would show a low solubility in heptane. Okay, and then moving on to volatility, compounds with high ionic character tend to have low volatility because strong ionic bonds require more energy to break, which prevents them from evaporating easily. And if you did not know, volatility is the tendency of a liquid to change into a gas. So this one would be low, and that would give us our answer of C. Number 7 says, what are the IUPAC names for CuBr and CuO? Remember, copper is a transition element, so it can assume multiple oxidation states. So we need to use the anion to figure out the charge of the cation or the transition element. So if we're looking at bromine, bromine is in our group 17 elements, which means it has a negative 1 charge. That would mean that our copper has to have a positive 1 charge. So our answer would be copper 1 bromide. So it would either be B or D. So let's move on from there. Then we have copper and oxygen. Oxygen's in group 16, which means it assumes a negative 2 charge. If oxygen is negative 2, copper would have to be positive 2 to balance that out to 0, which means D would be our answer with copper 2 oxide. Okay, number 8 says, which of the following substances show predominantly ionic character? So remember, an ionic compound is going to be between a metal and a non-metal, right? For I, we have magnesium, which is a metal, and chlorine, which is a non-metal. that is definitely an ionic compound. So we know that's one of the answers. So we can go ahead and cancel out C. Then we have iron 2 chloride. Iron is in fact a metal. Chlorine, again, is a nonmetal, so it would also be an ionic compound. So then we look at 3, silicon tetrachloride. Now, tetra, right away, should kind of ring a bell in your head because when you're using prefixes like that, it's normally for covalent molecules, which is in fact a covalent molecule. So just based off that fact, you should know that the answer is A, 1 and 2. But just to make sure, silicon tetrachloride is going to show little to no ionic character. Number one, because it forms covalent bonds rather than ionic bonds. And that's because silicon and chlorine have a very low difference in electronegativity, and they don't have enough difference in electronegativity to transfer those electrons. So instead, it's going to share those electrons with chlorine and form covalent bonds. The next is its structure. So you have silicon sharing 4 of its valence electrons with chlorine, forming a tetrahedral molecule. So that would not be an ionic compound. 3 would be a covalent compound, which shows little to no ionic character. So A is the answer for this one. 9. Explain why the melting point of magnesium oxide is higher than that of barium sulfide. So when we're talking about 2 ionic compounds, remember magnesium oxide, magnesium is in the second group, so it's going to form a 2 positive charge. Oxygen is going to form a 2 minus charge. Barium's down here, also 2 positive charge. Sulfur, also 2 minus charge. So we're not really focusing on the charge in this one in terms of Coulomb's law. We're going to be more focusing on radius. So if the radius is smaller, remember, it's going to have a stronger attraction, which is going to increase the lattice energy. And when you increase the lattice energy, that means it's going to require more force to separate those ions in an ionic compound. So if we're looking at magnesium to oxygen, obviously magnesium and oxygen are going to be much smaller molecules. Their radius is going to be much smaller, which means their lattice energy is going to be much higher. So let's go ahead and look at what IB had for this mark scheme. So this question was worth 3 marks. The first mark is that you had to essentially state Coulomb's law. So there is an electrostatic attraction that increases with charge and decreases with distance. To get the second mark, you had to say that magnesium ion had a smaller radius than the barium ion, and the oxygen anion had a smaller radius than the sulfur anion. And then the last mark was that the ionic radius of magnesium oxide is smaller than barium sulfide. Okay, so 10 says iron forms many compounds with water. Describe the bonding in Fe2O3. Now we know Fe2O3 is an ionic compound because you have a metal and a nonmetal, but it doesn't say explain or state the type of bonding. It says describe the bonding. So instead of saying ionic bonding, we would say an electrostatic attraction between your cation and your anion. And if you did not know how to get that iron was a positive 3 charge, you could either do the reverse cross method, which would mean oxygen's a -2, which we already know, and iron is a positive 3, or you could just use deductive reasoning. We know that oxygen's -2, and there are 3 of them, so I've given us an overall charge of -6. If the anion side is -6, the cation side has to be +6, and since we only have 2 iron atoms, each one would be a positive 3 charge. So the next part says state the full electron configuration of the bonding species. Now the bonding species are the ions, so if you just did the electron configuration for iron and oxygen, that would be incorrect. However, I am going to show you that to begin with, just so you understand where I got these electron configurations. So starting with iron, we know iron is here on the periodic table. If we did the electron configuration for just iron, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6. Now, Fe3 plus means that it lost electrons, right? If it lost electrons, it's going to lose the valence electrons first, which are the 4s electrons. So those are going to be gone. And then we need to take one more from the 3d sublevel. So our new electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and 3d5. Now let's do the same thing with oxygen. Regular oxygen would be 1s2, 2s2, and 2p4. But it says it gained 2 electrons. So now instead of 2p4, it would be 2p6, or the same electron configuration as neon. And then the compound Fe2O3 was previously known as ferric oxide. State the IUPAC name for the compound. Remember, for ionic compound naming with transition metals, we do need to place a Roman numeral there for the charge of our cation. Now we know the charge of our cation is 3, so we can go ahead and name it iron 3 oxide. And then I'm going to go to the next slide with the mark scheme so that you can go ahead and get the answers for D and E. All right, D says explain why iron 3 oxide can demonstrate brittleness. Ionic compounds demonstrate brittleness because when you apply force to them, it moves the layers so that charges of the same magnitude are next to each other, like your cations or your anions. And when they are forced to be closer to each other, that means that they are very repulsive. There's a lot of repulsion going on between those same charged ions, and that's going to make the compound brittle. And then E says that Fe3O4 contains an additional ion of iron. Identify that ion. Well, if you took Fe3O4 and subtracted all the compounds or the atoms that are in Fe2O3, you would get FeO. And when we have FeO, we know oxygen is a 2 negative charge, which means iron is a 2 positive charge. So that extra iron ion that's in there would be Fe2+. All right, describe the structure and bonding in potassium sulfide at room temperature. You should know that potassium is a metal, sulfur is a nonmetal, so that's going to be ionic bonding or an ionic compound. When you have a structure of an ionic compound, it's going to be a lattice of ions. And your bonding is going to be an electrostatic attraction between your potassium ions and your sulfur ions. For B, it says state the full electron configuration of the bonding species. Potassium plus, we know potassium ends in 4s1, but when it became an ion, it got rid of that 4s1 and went to the previous noble gas. So it has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Then we have our sulfur with a -2 charge. This ended in 3p4, but it gained 2 electrons. So it now has this exact same electron configuration as the potassium ion. So when we're talking about C, which is compare the size of the bonding species, they have the same number of electrons, and they have now the same number of energy levels, but potassium has more protons. And when it has more protons, that's what we call a larger nuclear charge. That means it's going to attract those electrons stronger and going to require a smaller atomic radius. So S2- is going to be larger than K+. And then finally it says describe and explain the electrical conductivity of solid and molten potassium sulfide. We've talked about this a few times. Remember, with ionic compounds, when it's a solid, it is not going to conduct electricity because there are no mobile ions to carry that charge. And then when it's molten, it is going to conduct electricity because now it has mobile ions when it's in that molten state. All right, the last question in structure 2.1 is number 12. It says successive ionization energies of calcium in a transition element X are shown. You see the blue is your calcium and the green is your transition element. For Calcium, you can see that there is a large jump going from the second to the third element, which should make sense because calcium has 2 valence electrons. Once it gives those up, it goes to the full third energy level, which requires more energy to remove an electron. Now, looking at our X element, I can kind of figure out that this is vanadium because after the 5th electron, it's going to require a very large jump in ionization energy. So I'm just assuming it's vanadium, which means after the 5th electron, if there's a big jump, that means it's going down to a previous stable sublevel, right? So that can mean that our maximum oxidation state for X would be a positive 5 because of that large jump in ionization energy. Now then B says to deduce a formula of an oxide of X in this oxidation state and explain why it's unlikely to be ionic. So if X has a positive 5 charge, we know oxygen has a 2- charge. That would form X2O5. Now this is unlikely to become ionic because that cation has such a large charge density that it would polarize the anion and would show covalent character. So think about it this way. If you have something with 5 valence electrons, it's very unlikely to get rid of all of those electrons. It would take a lot of energy. So it's more likely to do something else that's going to require a lot less energy to do. So that's why it would be unlikely to be an ionic compound. And then C says identify the ions X forms in its ionic compounds. Now, I'm sure there's a different way to do this. This is just what made sense in my mind. I looked at the 3 transition metals that were in the same group as vanadium, so V and B and TA, and I looked at their oxidation states in the IB data booklet, and obviously you can see that all of them can form a positive 5 oxidation state, but the other 2 oxidation states were 2+ and 3+, and that was my answer for this question. And if you would like it, here's the actual mark scheme for those 3, A, B, and C. All right, so now moving on to structure 2.2. Number 1 says, which bonds are arranged in order of increasing polarity? Remember, polarity is going to be the difference in electronegativity between 2 atoms. So all of these molecules have hydrogen in them. And then we're looking at the difference between our 4 halogens, fluorine, chlorine, bromine, and iodine. If we are looking at fluorine, we know fluorine is the most electronegative element on the periodic table. The difference between fluorine and hydrogen would be a difference in electronegativity of 1.8. And then hydrogen to chlorine would be a difference of 1. And then hydrogen to bromine would be a difference of 0.8. And hydrogen to iodine would be a difference of 0.5. So you can see the most polar molecule is going to be hydrofluoric acid, and your least would be hydroiodidic acid. So the answer would be C because it said increasing order. So HF would have the highest, HI would have the lowest. Which row correctly describes the bonding type and melting point of carbon and carbon dioxide? Remember from last section, carbon is going to be a covalent network solid, which is essentially means that all the carbons are connected by covalent bonds. So it's essentially one giant covalent molecule, which requires a lot of force to break apart, which coordinates to a high melting point. So for carbon, we are looking at a covalent bonding and high melting point. So that would automatically give your answer of A, but let's just double check that carbon dioxide is correct as well. We know that carbon dioxide is a covalent molecule, so we know it does partake in covalent bonding. And because it's a covalent molecule, it's not a covalent network. It's going to have a relatively low melting point because it's only being held together by its intermolecular forces, which in this case would be London dispersion forces. So this is also correct, and that would give us A as our answer. 3, what is the correct order of increasing boiling points? So we're looking at ethane, ethyl chloride, ethyl bromide, and ethyl iodide. And the key between looking at all of these is both considering the dipole-dipole forces that 3 of them have, and then the London dispersion forces that all of them have. So we know that ethane, or CH3, that's only going to have London dispersion forces, and our other 3 molecules are going to have both London dispersion forces and dipole-dipole because they are polar molecules. But when we're looking at increasing boiling points, if we look at the difference in mass between chlorine, bromine, and iodine, that is a significant amount of mass being added. So as you increase the amount of mass, not only are you increasing your dipole-dipole forces, but you are significantly increasing your London dispersion forces, which is why your ethyl iodide is going to have the highest boiling point because it has the most polarizable electron cloud, leading to the strongest London dispersion forces. So A would be your answer because you should know automatically that your ethane is going to have your lowest boiling point, so that actually cancels out B, C, and D right away, but that is the correct order. 4 says, which compound forms hydrogen bonds in the liquid state? Remember hydrogen bonds? Vanessa came up with F-no, if you want to remember it that way. Hydrogen bonds only occur when a fluorine, oxygen, or nitrogen is bonded to a hydrogen. And the reason that it partakes in hydrogen bonding is because it's an extremely electronegative element with lone pairs that is extremely attracted to hydrogens and other molecules that are bonded to very electronegative elements and create this really strong attraction for each other. So when we're looking at compounds that form hydrogen bonds in a liquid state, you need to look for a Lewis structure that has oxygen, nitrogen, or fluorine connected to a hydrogen. So if we look here, this is a telltale sign that that hydrogen is connected to the oxygen. So if you see OH at the end of any of the molecules, you can assume that it's going to partake in hydrogen bond because it means that that O has an H attached to it. And then you have your hydrogens here on the molecule. So this right here is what is participating in the hydrogen bond. So A would be your answer. This doesn't have oxygen, nitrogen, or fluorine. And this nitrogen does not have a hydrogen attached to it. So these would not be correct. And C would not be correct because we have a carbon with 3 hydrogens. And then this H is here to signify that it's on the carbon. So this carbon has an H here and then a double bonded oxygen. So you can see that this oxygen does not have a hydrogen attached to it, which means just a full sample of this would not partake in hydrogen bonding. 5 says, which molecule has non-bonding lone pair of electrons around the central atom? Boron has 3 valence electrons, so when it bonds out to 3 terminal atoms, there's going to be no lone pairs on that boron, which is why it's trigonal planar. So BF3 would not be an answer. SO2, sulfur, has 4 valence electrons, so it's going to bond all 4 to the oxygens, which means it does not have a lone pair on the central atom. Then we have BeCl2. Be, or beryllium, only has 2 valence electrons, so it's going to donate or share those with chlorine. So beryllium also does not have a lone pair on the central atom, which by default would be D, but let's go ahead and figure that out first. So silicon has 6 valence electrons. So if it had 4 fluorines to bond to, that means it bonded out 4 of its electrons. and had 2 left, so it's going to have a lone pair on the central atom. So that one would be our answer. All right, so number 6 talks about a coordination bond. IB uses 3 different terms for this type of bond. Make sure you write it in your notes because you never know which one they're going to use. They call it a coordination bond. They also call it a coordinate covalent bond, and it's also called a dative bond. So all 3 of those terms can be used interchangeably, so make sure you know those 3 terms. A coordinate covalent bond or a dative bond is a covalent bond that forms when both electrons come from the same atom. So when I am looking for which has a coordination bond, me personally, I look at for what bonds are supposed to look like, quote unquote. And then if they are bonded in a different way than they're usually supposed to be bonded, then I kind of assume that it's a coordinate covalent bond. But I'll show you more specifically what I mean. So if we're talking about HCHO, that means that I have a carbon with 2 hydrogens and an oxygen, right? Now this, every single atom is bonding how it's supposed to be, right? Carbon has 4 valence electrons, so it's supposed to have 4 bonds. It does have 4 bonds here. Hydrogen only has 1 valence electron. It's only supposed to have 1 bond. Both of these have 1 bond. Oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6. It wants, ideally in a perfect world, to have 2 bonds and 2 lone pairs. And in this molecule, it has 2 bonds and 2 lone pairs. So for I, or HCHO, I do not see a coordination bond because I know that all of those atoms only shared 1 electron in all 4 of those bonds in that molecule. Now, CO is carbon monoxide, right? Carbon monoxide is a carbon and an oxygen, and there's a triple bond with a lone pair on each of the atoms. Now, I know that carbon has 4 valence electrons, yet there is a total of 1, 2, 3, 4, 5 coming from carbon, which means that oxygen actually took one of its lone pairs and donated it as a bond between carbon and oxygen. So I know that carbon monoxide does in fact have a coordinate covalent bond. Now I know that H3O plus is going to be an oxygen with 3 hydrogens, and the plus would be this oxygen. Now, it didn't always used to be like that. Before it became this, most likely it was a water molecule with an H ion. And what happened was this oxygen donated its lone pair as a bond between the oxygen and the hydrogen, which formed this H3O plus. So both CO and H3O plus have your coordination bond, which means C would be your answer in this case. All right, so this was definitely a typo in the textbook. If you were looking at the HL textbook in class, it says octahedral shape. With these same answer choices, none of these 4 are a trigonal pyramidal shape or triangular pyramidal shape. So it was definitely a typo. Oxygen with 2 hydrogens, as we know, water, has a bent shape. Carbon tetrahydride or methane has a carbon with 4 terminal atoms. It's going to be tetrahedral. Aluminum fluoride is actually a ionic compound, so it's not going to have VSEPR shape or molecule. That would be an ionic compound. And then finally we have SF6. SF6 has 6 fluorines off the central atom, which is in fact an octahedral shape. So SF6 would be the answer. Just know on the textbook online that I posted for your teams says triangular pyramidal, which is not an option choice here. So change that to octahedral. The answer is D. 8. Which substance can form intermolecular hydrogen bonds in the liquid state? Remember we talked about look for that OH. Immediately you should notice that B has your OH, which means the oxygen is connected to a hydrogen, so that would be correct. The reason A is not correct is because the oxygen is in between the two carbons. So it looks something like this with your 3 hydrogens on the outside carbons. And because this oxygen is not connected to a hydrogen, it will not partake in hydrogen bonding in the liquid state. And D should be an automatic cancel out because there's no F, N, or O in the molecule. And then the reason C is not hydrogen bonding is because the H is connected to the C and the O is double bonded to the C. So it would look something like this, which clearly shows that oxygen is not connected to a hydrogen. So B is the correct answer. Number 9 says which calculation would be required to calculate the retardation factor value for spot 1 in this chromatogram. So the RF formula is over here on the right. In the numerator, you have the distance traveled by the solute. So in this case, we're looking for spot 1. So that would be Y in the numerator. And then the denominator, it's the distance traveled by the solvent or the solvent front. In this case would be X. So your answer would be Y divided by X, which is B. All right, based on the types of intermolecular forces, explain why butan-1-ol has a higher boiling point than butanol. So when we're looking at naming IUPAC for organic molecules, remember but stands for 4 carbons, meth, eth, prop, but. So for each of these, we're going to have 4 carbons in the carbon chain. And then it's telling us that the endings are different. For butan-1-ol, OL, that means it's an alcohol group, which is OH, right? So we know there is an OH at the ending of this molecule. And this one has an ending al, which is an aldehyde. And an aldehyde is essentially a carbon with a double bonded oxygen and a hydrogen, and it's attached to a carbon chain. So the difference between these two is not much besides the way that that oxygen is bonded. Now remember, we've talked about this a few times on these videos. Because this oxygen is connected to a hydrogen, this would partake in hydrogen bonding, which would create a lot stronger intermolecular forces between the molecules that would require more force to break apart, leading to a higher boiling point. And then with this molecule over here, this oxygen is not connected to a hydrogen, so just by itself, it could not partake in hydrogen bonding. And here is the actual mark scheme for this question. Number 11, for each of the species BH3 and PCl3, deduce the Lewis formula, predict the shaped and bond angle, and then predict and explain the molecular polarity. So remember boron in BH3, boron only has 3 valence electrons, so it's only going to form 3 bonds, and there's going to be no lone pairs on boron. So what that means, it's going to have significantly different shape and bond angle and polarity than PCl3, because phosphorus has 5 valence electrons, meaning that it's going to bond out to those 3 chlorines, and then it's going to have a leftover lone pair on the phosphorus, which is going to create polarity and shift the bond angles a little bit differently to minimize repulsion. So here is the explanation in the mark scheme for those two molecules. All right, so 12 says carbon and silicon belong to the same group of the periodic table. Describe and compare three features of the structure and bonding in the three allotropes of carbon, diamond, graphite, and fullerene. Now, the first thing that I want to make sure you understand is all three of them are technically covalent networks because they are all covalently bonded to each other, creating this one big giant molecule. But diamond is going to be the strongest, which you should know from just common knowledge. It's going to be the strongest because all four of its electrons are bonded out. So every single carbon has 4 bonds to other carbons in the molecule. So if we're talking about like electrons, carbon in diamond is going to have a sp3 hybridized bond. Because it has an sp3 hybridization, it's going to have a 3-dimensional tetrahedral structure, which just means that each carbon atom is covalently bonded to 4 other carbon atoms. Now, because in a diamond, carbon molecules are sp3 hybridized, the bond angles for carbons in a diamond are going to be 109 degrees, which would be different from graphite and fullerene. Now, the structure for graphite is going to essentially look like a layered structure, which is 2-dimensional. So you would have to say something like 2-dimensional structure, or you could write layered. Either one would work. I personally would write 2-dimensional. And then for your graphite, that's going to have an sp2 hybridization because it's only bonded, like one carbon's only bonded to 2 other carbons, and then this would connect to another hexagon, if that makes sense. So each one is sp2 hybridized, which would give you a bond angle of 120 degrees. And then finally, your fullerene, that's going to be spheres of atoms that are arranged in hexagons. So spheres of atoms arranged in hexagons. And then for your fullerene, it can take on sp2 or sp3 depending on the carbon that you're looking at. So for fullerene, you're going to put sp2 and sp3. So your angles are going to vary from 109 degrees to 120 degrees. And then the comparison between all of them is that they're all going to have covalent bonds and London dispersion forces. So this is going to be the actual mark scheme. It gave you an overall of 6 points. Then moving on to B, it says both silicon and carbon form oxides. Describe the structure and bonding in SiO2. So remember, SiO2 is silicon dioxide, which is that network solid. You could also say a macromolecule. And that means that every single one of those silicon atoms are going to be bonded covalently to 4 oxygen atoms. And it's going to create that very large molecule, which is a covalent network. And then explain why silicon dioxide is a solid and carbon dioxide is a gas at room temperature. Well, remember, silicon dioxide is a covalent network solid, which means that it's going to require a lot of force to break apart, which is why the boiling point or melting point is so high, and that's why at room temperature it's going to be a solid. Whereas carbon dioxide is just a non-polar molecule. It only has London dispersion forces, which means the intermolecular forces between them are actually pretty weak. And so at room temperature, it's going to exist as a gas. And then for C, describe the bonding within the carbon monoxide molecule. We know between carbon and oxygen there's going to be a triple bond, which we already did on a previous question, and that one of those electron pairs from oxygen were donated to carbon as a bond so that carbon could have a full octet. Methoxymethane and ethanol have the same relative molecular mass. Explain why methoxymethane has a much lower boiling point than ethanol. I know we already talked about this, but I'm just going to make sure that we completely understand. When we are talking about intermolecular forces, the strongest intermolecular force is going to be hydrogen bonding, and hydrogen bonding can only occur when you have F, N, or O connected to a hydrogen in the molecule. In methoxymethane, the oxygen is not connected to a hydrogen, whereas in ethanol, we do have an alcohol at the end, which is an OH group. And because that oxygen has a hydrogen connected to it, it's going to be able to participate in hydrogen bonding, which is a stronger intermolecular force than methoxymethane has. And that is why methoxymethane has a much lower boiling point than ethanol because of the hydrogen bonding. All right, so it wants us to get the Lewis structures, the shape, and the bond angles for these three species. The first one is NH3, which we should all be pretty confident at this point. We have nitrogen with 3 hydrogens, which is going to give us a trigonal pyramidal shape. Now remember, with our trigonal planar shapes, all 3 terminal atoms are on a plane, like with BH3, which means if we take 360 degrees and divide it by 3, the bond angles for those 3 terminal atoms are going to be 120. Now, if you take the terminal or the central atom and put a lone pair on it, it's going to create a different plane, which is going to force those 3 terminal atoms down and towards each other a little bit. So those bond angles are going to decrease. So now with a trigonal pyramidal, you're going to write less than 109 for your bond angles. Then for B, we know we have an overall charge of negative. This is how IB wants you to write the charge. It does not want you to write the charge next to the actual charged atom. So please do it like this. We know we have nitrogen and we know we have 2 hydrogens. And to keep the octet rule, this nitrogen would have 4 electrons or 2 lone pairs. Now, this is very similar shape to oxygen, so you should know that this shape is bent. And this would also have a bond angle of less than 109. And then finally, our last structure would be NH4, which means we have 4 hydrogens bonded to our nitrogen and an overall charge of +1. This would be a tetrahedral molecule. And with tetrahedral, your terminal atoms always have the angle of 109.5 degrees. So please make sure you have that memorized. 15, state the electron geometry and the molecular geometry and predict the bond angles for the following species. So first, let's go ahead and draw our Cl2O. O is going to be in the center, and then we have our Cl molecules on the outside. That is going to be a bent structure, and the angle is going to be less than 109. Then for the NO2 plus molecule, we have a nitrogen in the center, we have 2 oxygens, To keep your oxygens happy, we're going to just double bond those. That would give us a positive charge on the nitrogen. We're going to put that on the outside. Because there are no lone pairs on the nitrogen, that's going to be a linear molecule, which would have a bond angle of 180. Then it says for B, explain using diagrams why NO2 is a polar molecule, but CO2 is a non-polar molecule. So for NO2, if we did NO2, that would mean that we have one double bonded oxygen, one single bonded oxygen, but the charges balance out to 0. However, when we look at the dipole on this, the dipole would be going down or not canceling out. This would be a polar molecule. And then for CO2, the dipoles cancel each other out, which is why it is a non-polar molecule. And then for C, describe the structure and bonding in silicon dioxide. Again, this is on a lot, so obviously it's going to be on the exam. Silicon dioxide is a network covalent solid or a macromolecule. Its bonding is all single covalent bonds. Ethyne and ethene are both examples of hydrocarbons. I remember when we're talking about naming organic compounds, eth is the prefix for 2 carbons, which is why both of them have 2 carbons. Yne means that there is a triple bond. Ene means that there is a double bond. So for ethyne, that would look like this. And for ethene, that would look like this. So that would be the answer for A. And then it says, compare, giving a reason, the length of the bond between the carbon atoms in ethyne and ethene. The length in the triple bond is going to be shorter because there are more electrons pulling at each other. So it's going to be a stronger electrostatic attraction to the nuclei. So the bond in ethyne would be shorter than the double bond in ethene. And then finally, identify the type of interaction that must be overcome when liquid ethyne vaporizes. That's just going to be London dispersion forces because they are nonpolar molecules. So we did already talk about this retardation factor with paper chromatography. So I'm going to let you pause this one and kind of just read through this one on your own. If you have any questions from structure 2.1 and 2.2, please feel free to come in during office hours on Wednesdays before and after school. I'm always willing to help you, and I hope that this video helped. Have a great day. Go Rams!